Well, good morning, class. I don't know if it's morning where you are, but it's morning where I am today. We're going to continue now with a new chapter. This chapter is on chemical bonding and reactions. It really is a continuation of the chapters we've been covering on matter. If you remember, a couple of chapters ago, we talked about the basic components, the basic building blocks, the atoms and elements, the elements on the periodic table. And then we took a sort of a deep dive into the very small and the very fast, and we talked about quantum behavior, quantum mechanics, the behavior of electrons in particular in atoms, which are sometimes amazing and surprising. Now we're going to go back and talk about things that are a little bit more practical perhaps, but how atoms bond together to form molecules. Chemical reactions are important because when matter reacts, it forms something new. In some cases, this can be desirable as we try to synthesize or prepare new materials. In other cases, it can release energy or require energy. And in yet other cases, we may want to limit or prohibit the reactions in order to keep some material from decaying or oxidizing. For example, we would like to prevent our silver from being tarnished. And so for all of these reasons, we study chemical bonding and chemical reactions. And on this first slide, I show a slogan, which is really an alternative to one used by the DuPont Chemical Company for a number of years: better living through chemistry. Also, before going into the next slide, I'll mention that chemistry is oftentimes called the central science, both because of the size range between the extremely small and the extremely large, and also because matter and chemicals are used in essentially all other fields of science, from cooking to metabolism, to understanding the chemistry of our bodies, to making new materials that are used in engineering, etc. Now, a little bit of a recap. If you recall, in the chapter on atoms and the elements, we talked about the periodic table, and we said there are about 114 of these, maybe a few more, and about 90 of them are naturally occurring. That means they are found in nature. The other 20 or so that are at the bottom of the periodic table are man-made. But what was really important for us to understand is the trends of reactivity. And basically we can sum this up as that the things on the left react with the things on the upper right. The elements on the left are called metals, the ones in blue, and the ones in the sort of reddish color are called nonmetals. Now, basically, these are the players of the game, the 90 to 114 players of the game. We really only deal with the first 2 or 3 rows in the periodic table for most chemistry that we will deal with. But the metals tend to want to lose electrons. The nonmetals tend to want to gain electrons. And that tendency explains a lot of the behavior of elements, explains a lot of chemistry. Each is actually attempting to achieve a filled outer shell of electrons. Now let me explain what that means. If you look at the first row in the periodic table, there are only 2 boxes, or 2 elements that exist in what we call energy level 1. That is the first row, hydrogen and helium. So once we get to 2 electrons, we have the element helium. But let's continue to the next row where things get a little bit more interesting. The next row, there are 8 boxes or 8 elements in the second row, which we also call energy level 2. Lithium, beryllium, and then going over to boron, carbon, nitrogen, oxygen, etc. And if an element has 2 electrons from the first energy level plus an additional 8 for filling out the second row, it now has a total of 10 electrons. That element that has 10 electrons is neon, and it has electrons that completely fill both the first energy level and the second energy level. Continuing on to the third row, or the third energy level, again there are 8 elements in row 3. And so if an element has 2 electrons from the first row, 8 from the second, an additional 8 for filling out the third energy level, it would have a total of 18 electrons. That would be argon. And likewise, if we go to the next row, it actually gets even more complicated because we have to fill in what are called the transition metals. And so a filled outer shell of electrons would have 2 from the first row, 8 from the second row, 8 from the third row, and 8 from the fourth plus 10 from that fourth row, giving a total of 36 in order to form krypton. Now, these are sort of the numbers of electrons needed to completely fill each energy level. This is sort of like playing a game of cards in which you either want to have a pair, 2 cards in your hand, or a pair plus 8 cards, total of 10, or a pair plus 8 plus another set of 8 to have 18, or 2 cards or a pair plus 8 plus 8 plus 8 plus another 10 to have 36. That is, you want to have these set numbers of cards in your hand. Now, as with playing cards, in order to achieve these numbers of 2, 10, 18, or 36, you could either lose electrons or lose cards to get to these numbers, or gain electrons, gain cards to get to these numbers. And so that basically explains the tendencies. Now you'll notice that the number 8 shows up a great deal. And so if you've heard of the octet rule, that's why. That's because actually in rows 2 and 3, you'll notice that there are 8 elements across those rows, and that is basically the origin of what we call the octet rule. Now there are 2 basic types of bonding that occur between atoms. One we call ionic bonding, and the other we call covalent bonding. Now there's a range of bonding in between, but the 2 extreme types are called ionic bonding and covalent bonding. In this first lesson, I'm going to talk about ionic bonding. Let's consider sodium. Sodium, which has 11 electrons. And remember, one of those important numbers was 10. So sodium has 1 electron in its outer shell, sort of by itself. And we oftentimes represent that by drawing sodium in the following way, with just showing 1 extra electron in an outer shell by itself. So sodium has a tendency to want to lose that electron. Chlorine has 17 electrons, 7 of which are in its outer shell, which we represent as shown here. Now, remember, one of those important or magic numbers is 18. So chlorine would have a tendency to want to gain an electron. So, if sodium and chlorine could get together and sodium would transfer one of its electrons to chlorine, then they would both be satisfied. Sodium would now have 10 electrons in its outer shell. Chlorine would now have 18 electrons, and in each case they would have filled their outer shell of electrons. In doing so, sodium, when losing electron, would become a cation, what we call a cation, sodium plus 1, and chlorine would become what we call an anion, a negatively charged species, chloride minus 1. Now, oppositely charged species, you may have heard that opposites attract, and this is the basis for that saying. From Coulomb's law, we know that oppositely charged species will attract each other. This is an electrostatic attraction, what we call Coulomb's law. And so after the sodium has become a cation, a plus 1 species, and chlorine has become chloride, a minus 1 species, they now attract each other by this electrostatic or Coulombic attraction. They essentially hold hands in what we call an ionic bond. So this is the basis for forming an ionic bond. Now let me show you the consequences of forming such a bond by illustrating how the properties of sodium chloride are distinctly different from the properties of sodium metal and chlorine gas. Sodium metal is a very reactive metal. In fact, it ignites when dropped into water, and it will actually, you will have a little pop and explosion. That's why in the graphic, the person holding the sodium is wearing gloves, and generally we store sodium in oil to prevent it from interacting with water. Chlorine, shown in this glass vial, is a green gas, and it's very reactive, very poisonous. So we would not want to come into contact with either sodium metal or chlorine gas. But yet, when these two elements react to form sodium chloride, this becomes common table salt. And we find it in salt shakers, all restaurants and in our cafeterias, and we generally think
anyone
it's
likes
pretty safe.
fries with their sodium chloride.
So this is an example of ionic bonding and the resulting compound that can be formed. Now, I said that there are two extreme types of bonding, ionic bonding and covalent bonding. But before going into covalent bonding, I want to also mention another type of bonding called metallic bonding. Now, metallic bonding is a property of metals, and it actually helps us understand, or it helps explain a number of the properties of metal, in particular how metals can conduct electricity, their tensile strength, their high melting point, etc. In the solid lattice structure of metals, we consider the electrons to be mobile. That is, instead of being localized around each of the nuclei, which are represented as the positive gray balls in this graphic, the electrons, the red species, are thought to be able to swim through or to hop between the metal cations. And the ability of electrons to move in this way stabilizes the lattice structure of metals, but also is the mechanism for electrical conductivity, and it also helps explain some of the thermal conductivity and other properties of metals. Okay, we're going to pause now, and you'll have a little quiz, and then we'll return and we'll talk about covalent bonding. But before we take our break, I thought maybe you'd want to hear a story about lithium and sodium, both on the left-hand side of the periodic table, very reactive. Early one Sunday morning, that fine divide between Saturday night and Sunday morning, lithium and sodium are headed to church, and sodium says to his friend lithium, "Had a rough night. I met up with the chlorine sisters last night, and I think I lost one of my electrons." And lithium asks his friend sodium, said, "Are you sure?" And sodium says, "Yes, I'm positive."